Hello students, today we are going to start the next chapter, chapter 3, exponential and gamma distribution. So exponential and gamma distribution, this is the example of again continuous distribution. So students in real life situations, not all times situations are of symmetric cases. So there are some cases where the asymmetric distribution may be follows. So this exponential distribution and gamma distribution, this is example or this is the case of asymmetric distribution. So some of the common examples of this exponential and gamma distribution is, or some of the common example of this exponential distribution is the lifetime of any electronic component. Then secondly, we can discuss the time until decay of radioactive atom. Third example is inter-arrival time, customers in between the queue. So these are the situation where the exponential distribution is satisfied. So let's start its analytical discussion. The content of our today's lecture is we will discuss the definition of exponential distribution. We will find out moments. On the basis of that moments, we will find out the raw moments. And we will derive the expression for MGF. With that expression, we will find out the raw moments. After that, we will find out the derivation or the expression for CGF. With the help of this expression of CGF, we will find out cumulants and hence we will find out central moments. And on the basis of that, we will interpret about the nature of the distribution. After that, we will also find out distribution function and median and quartiles. So this is the content of our today's lecture. Let's start the session. Call the definition. Let capital X be any continuous random variable is said to follow exponential distribution with parameter theta if its PDF is given by PDF is given by so its PDF is f of x is equals to theta into e raised to minus theta x. X is positive, is also 0. Its notation is x follows exponential distribution with parameter. There is one more another form where we can use this PDF. Fx is equals to 1 upon theta into e to minus 1 upon theta into x. We will all the derivations or will derive all the expressions for this PDF theta into e to minus theta x only. Next, mean and variance. Let x follows exponential distribution parameter theta. F is theta into e raised to minus theta x x is positive then 0 then 0, 0 otherwise. Expectation of x is equals to integration x to fx dx over x. Put the value of PDF here. PDF is theta to e raised to minus theta x dx. Take this theta constant outside. So the x range of x is from 0 to infinity. X into e raised to minus theta x. Now compare this integration with gamma function or with this formula integration from 0 to infinity. E raised to minus ax x raised to n minus 1 into dx is to gamma n divided by a raised to n. So if you compare this with this formula, a is equals to and n minus 1 is 1. N is equals to, so put this value of a and n here. Expectation of x is theta into gamma 2 divided by a raised to n. A is theta. Gamma 2 is 1 factorial, so it is 1. Expectation of x is theta upon square is equals to 1. So the mean for exponential distribution is, if x follows exponential theta, then its mean is 1 upon. Similarly, we can find out variance. So to find out variance, first of all find out expectation of x square. So we will find out this expectation of x square on the same lines. X square fx equals to integration x square, the value of PDF, theta outside, e raised to minus theta x dx. Again use the same formula of gamma, is integration from 0 to infinity, e raised to minus x raised to n minus 1 into dx, gamma n upon a raised to n. So if you compare this with this given, a is theta and n minus 1 is 2, n will be 3. So put these values, so theta into gamma n, gamma 3 upon theta cube. Gamma 3 is 2 factorial. If you solve this, you will get 2 upon theta square. Expectation of x square is 2 upon square. And hence, variance of x is the values of e of x square and e of x, formula of variance. Solve this, 2 upon theta square minus expectation of x is 1 upon theta. So theta square. Variance of x is 1 upon square. Now, so if x follows exponential distribution with parameter theta, then the mean is 1 upon theta and variance is 1 upon theta square. Okay. Now, next is we will find out moments for exponential distribution. So moments we will find out by the formula. The raw moments, they are denoted by mu r dash. Is denoted by expectation of x raised to r is equals to integration x raised to r fx dx x raised to r. The value of PDF, take theta constant outside, e raised to minus theta x dx. Use the same gamma function formula, e raised to minus ax gamma n upon a raised to n. So here a is theta and n minus 1 is r. N will be r plus 1. Its answer is x starts from 0 to infinity. Mu r dash is equals to theta into gamma n, that is gamma r plus 1 divided by a raised to n, that is theta raised to r plus. So this theta upon theta raised to r plus 1 is gamma r plus 1 is r factorial divided by theta raised to r. This r starts from 1 to. This is the general expression for raw moments. Okay. So if you put the value of r is equals to 1, 2, 3, 4, you will get the different values of raw moments. So already we compute mu 1 dash. 1 dash is, if you put the value of r is equal to 1, is 1 upon theta. Mu 2 dash is 2 factorial, that is 2 upon theta square. Mu 3 dash factorial, that is 6 upon theta cube. And mu 4 dash is 4 factorial, which is 24 upon theta raised to. This way we can find out the moments using this general formula. Now the next concept is MGF, moment generating function. It is moment generating function. It is denoted by mx of t, and it is obtained by expectation of, this formula is expectation of e raised to tx, which is nothing but integration e raised to tx fx dx put the value of PDF here. E raised to tx fx is take theta constant outside, e raised to minus theta x theta into e raised to take minus sign constant outside, so this will be theta minus t x dx. So if you take if you use some simple substitution, u is equals to theta minus t, so will be e raised to minus ax. If you compare this with the same formula of gamma, you will get theta into x raised to 1 here, and minus 1 is equals to 1, n will be 0. So this is gamma 1 upon, this is a theta minus t raised to 1. So this is the MGF. If you solve this, take theta constant outside, this theta get cancel here. MGF for exponential distribution is 1 minus t upon theta raised to minus this t upon theta should be less than. Now this is the general expression for moment generating function. With the help of this MGF, we can find out the purpose of MGF is, with the help of MGF we can generate, we can obtain raw moments. So let's derive or let's express this MGF mx of t, obtaining raw moments using MGF. This is the expression of concept is obtaining moments, raw moments using MGF. Mx of t is 1 upon 1 minus t upon. So use the series. We have one standard series. It is 1 upon 1 minus x. It is equals to 1 plus x square plus x cube plus x raised to 4 and so on. So use this standard series. Treat this t upon theta as a x and solve this. So is 1 plus what is x here? X is t upon theta plus t square upon theta square and t cube upon theta cube plus t raised to 4 upon theta raised to 4 plus and so on. So this is the expression of MGF. And how we will obtain the raw moments using MGF? That is mu r dash are nothing but these are the coefficients of t raised to r upon r factorial in the expansion of u1 dash will be coefficient of t, and you can easily observe that coefficient of t here it is coefficient of on 1 factorial, that is coefficient of t, which is equals to 1 upon theta. U2 dash nothing but coefficient of square upon 2 factorial, which is nothing but coefficient of t square upon 2. So if you observe here, coefficient of t square upon 2 is here you have to make adjustment 1 plus t upon theta plus you have to multiply this by 2 factorial and divide it by 2 factorial. This is 2 factorial and here it is 2 square. Similarly, you can multiply here by 3 factorial t cube, this is 3 factorial, here it is theta, this will be 4 factorial t raised to 4 there is to 4 and is 4. So now you can easily identify here the coefficients. The coefficient of t square upon 2 factorial is 2 factorial upon theta square, that is 2 upon square. Mu3 dash is coefficient of t cube upon 3 factorial, which is nothing but 3 factorial upon theta cube, which is 6 upon theta cube. Mu4 dash is coefficient of t raised to 4 upon 4 factorial. T raised to 4 upon 4 factorial is 4 factorial upon theta raised to 4. Is nothing but 24 divided by theta raised to. This way we can obtain the moments by using MGF. So students, on the basis of moments also we obtain the moments. On the basis of MGF also we obtain the moments. What is the purpose? By obtaining these moments, we can find out the central moments so that we can interpret about the nature of the distribution. But by finding the moments with the help of these raw moments might be difficult than they are easy finding with the help of cumulants. So we will find out the central moments with the help of cumulants, not by these raw moments. Okay, so we will do that in our next expression. Now the next is cumulants, that is CGF. Full form is cumulant generating function. Cumulant generating function. So notation is kx of t is equals to log of mx of t is equals to log of mx of t is 1 minus t upon theta raised to minus 1. Take this sign minus 1 outside. This is minus log of 1 minus t upon theta. And now use one standard series, log of 1 minus x equals to minus the bracket x plus x square by 2 plus x cube by 3 plus x raised to 4 upon 4 plus and so on. We will use this series and we will expand this expression kx of t. X of t is equals to minus treat this t upon theta as a x. It is minus t upon, this is t upon theta plus upon 2 square upon theta square plus upon 3 t cube upon theta cube is 1 by 4 raised to 4 upon theta raised to 4 and so on. So this minus minus sign, log of 1 minus this minus and this minus, it will be plus. Which is equals to t upon theta plus 1 upon theta t, the coefficient of t raised to 1 upon 1 factor plus 1 upon theta square into t square upon 2, which is nothing but t square upon 2 factorial. To make this 3 as a 3 factorial, you have to multiply this by 2. So this is 2 upon theta cube t cube. If you multiply this here by 2, that will be 6, which is nothing but 3 factorial. This way we have to make these arrangements. Then to make this 4 factorial, we have to multiply this 4 by 6. To multiply and divide it by 6. So this is 6 upon t raised to 4 raised to 4 upon 4. So now easily we can compare this with the coefficients of. So the Kr is nothing but cumulants are the coefficients of e raised to r upon r factorial. The expansion of kx of t. So if you compare this, we will get k1, the coefficient of t is 1 upon theta. k2, coefficient of t square upon 2 factorial, which is nothing but 1 upon theta square. So k1 is always mu1 dash, and mu1 dash already we obtained 1 upon theta. k2 is mu2 variance. We already obtained mu2 as 1 upon theta square. k3 is the coefficient of t cube upon 3 factorial, which is 2 upon theta cube. So we know that k3 is nothing but mu3. K4 is equals to coefficient of t raised to 4 upon 4 factorial, which is nothing but 6 upon theta raised to 4. Okay, and now with these cumulants, these are the cumulants which we obtain with the help of this. And now with the help of these cumulants, we will obtain central moments. So mu1 is always 0. Mu2 is nothing but k2, uh, which is 1 upon theta square. Mu3 is equals to k3, which is 2 upon a cube. Mu4 is equals to now k4 plus 3 times square. K4 is 6 upon theta is to 4 plus 3 times 1 upon theta square square, that is 1 upon theta is to, which is equals to 9 upon theta is to 4. Okay. And now students, we are in the last part of our today's lecture, that is uh, we will obtain now the coefficient of skewness and kurtosis. Okay, then we stop for today. Coefficients of and the coefficient of skewness is gamma 1, which is equals to square root of beta 1, where beta 1 is mu 3 square upon 2 cube. Mu 3 is 2 upon theta cube square divided by mu 2 is 1 upon theta square cube. You solve this, 2 square is 4 upon theta raised to 6 divided by 1 upon theta raised to 6, which will be beta 1 is 4, gamma 1 is equal to square root of beta 1, which is equal to plus minus 2, but we will consider it simply 2. Why? Because all the values are positive, therefore this coefficient we will get this plus 2 here. Sorry. So beta 1 is 4, gamma 1 is equal to this, take this as a 2. Therefore we can interpret that distribution is positively skewed. And why we take this as plus values? Because xi's are positive here. So the distribution is, therefore exponential distribution is positively skewed. And also we can interpret, or we can discuss the sign of this gamma 1 on the basis of this mu 3 only. Mu 3 is 2 upon theta cube. So, with the help of this mu 3, we can interpret about the nature of distribution. So mu 3 is equal to 2 upon theta cube. We know that theta is positive, therefore this 2 upon theta cube is also positive. So from here also we can interpret that the exponential distribution is positively skewed. And the last is we are discussing the coefficient of kurtosis. This is the last part of our today's lecture. Coefficient of kurtosis, that is gamma 2 equals to beta 2 minus beta 2 is mu 4 upon mu 2 square. Put the values of mu 4 and mu 2. Mu 4 is 9 upon theta raised to 4. Mu 2 is 1 upon theta square. Its square is 1 upon theta raised to 4. If you solve this, you will get 9. Beta 2 is 9. Gamma 2 is equals to 9 minus 3, 6. It's positive. So the interpretation is exponential distribution is leptocritic. So here we have find out the coefficient of skewness and kurtosis. So in the next lecture, we will find out the distribution function and median and quartiles. We will discuss in the next lecture. So for today, we stop here. Thank you.